Okay, thank you very much. Good afternoon, everybody. And first of all, many thanks to Stefan and to Thomas for the invitation. And I'm very happy to discuss with you today some work we have done on mixed symmetry, tensor, gauge theories, and duality. So this is more physics-oriented talk. Nevertheless, I think it fits very nicely in this week's, in this focus week on supergeometry, because I'm going to show you some use of graded coordinates, which is slightly different from what we have heard so far. And let me say that this work is based on a number of papers with my student Yoros Karagiannis, who is also in the audience, and Peter Schupp from Bremen, but also to some extent in some older paper with Peter again, Diederik Rust, and Feksenku. So to start with, well, I don't really need this graded geometry teaser for this focus week, but just to remember a few things. So graded geometry, of course, has applications both in physics and mathematics. So in physics, of course, it's supersymmetry, and then the BV-BRST formalism, aka Z-sigma models that we have heard a lot about them in previous talks. But also in the context of Q-manifolds that we have also heard quite a lot, and Poisson geometry, Courant algebroids, and L-infinity algebras. But these are stuff that I'm not going to talk about today. Instead of that, I will kind of talk about something quite simpler and try to find some other applications of using graded coordinates. So here are the motivations and the goals of our work. So first of all, we are interested in these mixed symmetry tensor fields, which I will describe later, but you have already heard something about this on Monday in the talk of Henning Samtleben. And basically, we would like to find a better description of their Lagrangians, in particular their kinetic terms, maybe their mass terms and topological terms, and have a unified formalism that takes together these mixed symmetry tensors, P-forms, and then, of course, these mixed symmetry tensors include gravitons, include the Cartwright field, which is a 2,1 tensor that we heard about on Monday. And, of course, I should say here that most of the time I will be dealing with linear theories. Now, the second bullet point regards interactions. So, typically, the question here is what kind of interaction terms can we add in the effective field theory that can contain higher derivatives, but they still maintain second-order field equations. So I will discuss this later on, this question. And basically, the answer to this question was quite known in the last years for scalar fields and for P-forms. What we do is that we try to extend this for mixed symmetry tensors, classify what kind of interactions like that can exist, and present some universal Lagrangian that takes care of all these interactions for all these fields together. And the third thing is regards dualities. So dualities here is a word that I use in a more general sense. Apart from standard electric magnetic duality that we know between P forms and D minus P minus 2 forms, there are also possibly dualities for the graviton. There is this so-called double duality for the graviton. There are also exotic dualities, and even there has been an argument that there are infinite ways to represent a particular degree of freedom in terms of covariant tensors. So the goal here is to understand the systematic dualization procedure for all these types of dualities and maybe equivalencies, because sometimes this duality is not a real duality. I will discuss this towards the end of my talk. And of course, let me mention that mixed symmetry fields are interesting because they appear in formulations of string theory and M theory, and they are also argued to couple to branes, not D branes, but heavier branes in string theory, essentially. So this is mainly the motivation. So to start with the main idea, so it's very simple. We kind of heard it multiple times. So it's how to treat tensor fields as functions on a graded supermanifold. So for differential forms, this is easy. So we have, we just need a Z2 graded geometry. We need even coordinates xi and odd coordinates theta I, so degree 1 coordinates that anti-commute like this. And then, of course, we can describe differential forms or multivector fields as functions on graded bundles. This is also what Alexei was presenting in a more general setting this morning. So in particular, a function on the degree-shifted tangent bundle of manifold M can be expanded in these coordinates like this. So, and here we recognize the antisymmetry of these components, which is exactly the antisymmetry we expect from differential forms. And integration, in this talk, integration will be defined as usual by means of the Berezin integral. So I will be using Berezin integral, and I lost it. No, it's OK. I will be using the Berezin integral in the rest of my talk. Now, that's the story for differential forms. So then we ask what happens for mixed symmetry tensors. And then here I will concentrate on so-called bipartite tensors. So these are tensor fields that have two sets of coordinates which are antisymmetric in each set, but not cross sets. So essentially, they correspond to representations of the general linear group that have more than one columns as a Young tableau. So in particular here, two columns. So these kind of bipartite tensors, which I will call them of degree p, q, so these are the lengths of the columns, they can be described if one considers functions on essentially the direct sum of T1m with itself. And in this particular case, you will introduce two sets of odd coordinates. So it's a very simple generalization of the p-forms. So I will have a set theta I and a set chi I. So these are degree 1 coordinates. They anti-commute between themselves. And then I will choose the convention that they commute cross sets. So as long as you keep track of your signs correctly, you could either choose them anti-commuting or commuting. We choose them commuting in this work. So then you can describe a mixed symmetry, a bipartite tensor field by doing this expansion here in terms of theta and chi. And then, of course, you see that the components of these tensor fields inherit this mixed index symmetry. So they are antisymmetric in the p first indices, antisymmetric in the last q indices also, but not necessarily cross. And let me mention here that it's useful to think even of differential forms as a sort of degenerate case of bipartite tensors with one empty slot. Of course, this is sounds quite trivial, but actually it is very useful in applications. And of course, let me mention also that you can generalize this to n-partite tensors. So if you have more sets of antisymmetric indices, in which case you would have more sets of degree 1 coordinates. Good. And then on this kind of setting, you can start building some sort of calculus. So let me describe. Yes, please. There is a question.
Thank you. Yes, I have a question. Usually one imposes irreducibility conditions, that if you try to replace one chi by one theta, you get 0 or something.
I will discuss this
later. Okay.
Shortly, like in 1 or 2 slides.
Thank you.
Thanks. So first of all, one can define exterior derivatives that increase the degree of the bipartite tensor either in the first slot by 1 or in the second slot by 1. I would call them d and d twiddle. And d is essentially, well, what we would call a homological vector field. So it's given like this. Partialize the derivative with respect to the bosonic coordinates. And d twiddle is the same thing with the chi I. They both square to 0, and they commute in our conventions. Moreover, one can define a transposition map. Essentially, this is exchanging all thetas with all chi's, right? So this takes a p, q bipartite tensor and gives q, p bipartite tensor, which I will denote either with a tilde or with this transposition symbol that says that they exchange theta and chi. Good. Apart from this, one can define partial Hodge star operators. So this will be, so I call them partial because, of course, for a bipartite tensor, you might want to dualize along both slots. I will discuss this shortly. But here, let's think about these operations that dualize either the first slot from P to D plane P, or the second slot from Q to D plane Q. So there is a nice way to actually do this in intrinsic graded terms. So if I introduce an auxiliary set of odd coordinates, which anti-commute among themselves and commute with the thetas and the chi's, then the partial Hodge star operator is just transposing the bipartite tensor with respect, changing all thetas to psi's, and then saturating the Berezin integral in psi's so that you get deep psi's here by means of a Minkowski metric. In particular here, I will think the Minkowski metric as this symbol eta, which has the components of a Minkowski metric in theta and chi. Now, as you see, what I have done here in order to define the partial Hodge star in this intrinsic way is that essentially I have treated the Picot-Mathieu bipartite tensor as a tripartite tensor with a trivial slot, and the Minkowski metric is also as a tripartite tensor with a trivial slot. So here, when you see the transposition chi psi of eta, it means that I exchange chi with psi. So this is this. So now this is a graded geometric approach to the calculus developed by Chris Hall and de Medeiros and Hall nearly 20 years ago. Furthermore, unlike differential forms, bipartite tensors have traces. Right? Differential forms are already reducible representations of the general linear group, but not necessarily so for bipartite tensors. Trace can be defined in a very nice way. So essentially, you take the derivative with respect to the degree 1 coordinates. I will call this bar.
Athanasios?
Was a question? Yeah, that's Thomas.
Yes.
Yes, Thomas. Yes.
Yes, that's me. Just in the previous slide, this eta transpose, is it different to eta?
The eta transpose is eta. No, it's not different than eta. The components are the same. The components are the same. The transpose just says that I use different degree 1 coordinates. But this is a trick.
No, but this is just eta transpose is equal to eta or not?
The components of eta transpose is, so eta transpose, if you use the transposition in theta and chi, is exactly equal to eta. Yes.
Yeah, so you could drop this transpose at eta, yes?
Where? Now I missed the...
In the formula for star omega?
No, because here I do transposition, not between... so the transposition... Do you see my... I don't see my pointer, I lost it, sorry. No, I see it. Okay, I found it. So when you think of eta as 1,1, so like here, and I apply the transposition on theta and chi, then eta transpose is eta. But when I think of eta as a 0, 1, 1, and apply a transposition in the first and second slot, it's not exactly the same. That's the difference. It's a trick. Do you see the point?
No.
Okay, let me try again. So
no, I see. Eta transpose has instead of a chi, it has a psi. Now I see it. Okay. Yeah. Now I understand. Okay. And the power d minus p means this to the power of d minus p?
It's a power. Yes, it's a power.
Okay. Thank you. Mm-hmm. And the volume form your Minkowski space, I suppose, or what?
It's Minkowski, yes.
Yeah. Okay. Thank you.
Okay. So there goes the trace. The trace is given by this operator here. And then, moreover, one can define dual operations. First of all, d dagger will be something that decreases by 1 the first slot of the bipartite tensor, and the twiddled one will decrease the second one. And this, of course, is defined as usual. You can define it either as the partial star d partial star, and the same for d twiddle, the partial twiddle d twiddle. Or you can define it using the graded formalism here. It would be like this. So this is like the divergence, right? Moreover, one can define cotraces. I use here the notation that Chris Hall is using. So cotraces means something that takes a Picot-Mathieu bipartite tensor and spits out a p plus 1 q minus 1, or the twiddled one doing the opposite operation. So let me define sigma. Sigma is the partial star trace partial star. So it's like the dual operation to trace. This has a very nice incarnation in this coordinate, degree 1 coordinate form. It is just this. So sigma twiddle will be minus chi theta bar. And now these are important operators because, as Mark pointed out earlier, these give us a criterion for irreducibility of the tensor under the general linear group. In particular, for p greater or equal to q, the bipartite tensor is irreducible if the cotrace acting on it is 0. Moreover, if p equals q, you have the additional condition that the omega twiddle is equal to omega. So this is the irreducibility criterion. So if you want to work with irreducible fields, then you can start with the reducible one and apply some appropriate Young projector, which was found in this paper here, and it has this form here in terms of these cotrace operators. And then you know this is unique, and you know what is your irreducible field, and you can work with it. Now, however, in order to go to the direction of constructing Lagrangians, we would like to have some generalized Hodge duality operator. And I think this will become transparent in a moment. Well, first of all, if we want to construct a Lagrangian, we need an inner product, and the inner product for differential forms is controlled essentially by the Hodge star, so we need the analog for the bipartite tensors. And now, our proposal is that the generalized Hodge star operator should be defined like this. So you start with a p comma q tensor, and you construct a d minus p d minus q tensor, because eventually you are going to integrate over both theta and chi. So you want to have d thetas and d chi's in your integration in order for your Berezin integral to work. So the definition is then that you take the transpose, the twiddle operator on the field, and then you saturate it with a number of etas such that you get this degree, this by degree, and this, of course, is a standard factor. And, of course, you could ask me, well, if you want something that is d comma d eventually, why don't you use just the product of the two partial Hodge star operators? Because this is what they do also, right? But you can see that the product of the partial Hodge star operators is very different than this new operator that we define. And in fact, we have shown that the generalized Hodge on a p comma q tensor is given by the product of the partial ones on it, plus a finite number of additional terms that include the traces of the field. And of course, this is, this is the formula here. So this is a finite sum that includes these traces. Actually, this is a very welcome thing, I think, because the new operator also encodes all the traces which appear in the kinetic terms of this kind of fields. So then one can define a symmetric inner product for two bipartite tensors simply by this generalized Hodge star operator and by integration. So by this integration, I mean you integrate over thetas and chi's. This is Berezin integration. Which brings me now to the kinetic terms. So for differential forms, of course, we know how to write a kinetic term in a nice way. So this is just the standard inner product is this one. But then if you take a bipartite tensor in particular, if you take p and q1, so this is the graviton, essentially. So the linearized Einstein-Hilbert Lagrangian, which is the kinetic term for the graviton, looks like this in components. So this is significantly more complicated in a way than the standard p forms, which is just a single term. And moreover here, there are a number of factors which are fixed and a number of signs which are fixed. So one question is, can you write this Lagrangian in some form like this? And of course, this becomes even worse if you go higher. So even for p equals 2 and q equals 1, so there exists this Cartwright-Gauge theory, which was found by Thomas Cartwright in the 80s for the Hooke-Young tableau, which looks like this. So this is a 2,1 tensor, and the kinetic term looks like this. Again, with fixed factors and signs, which looks very complicated. So the point of our formalism is that these complicated formulas are actually nothing but this simple formula here. So you take a bipartite tensor, and you just use the generalized Hodge star to construct the kinetic term. So this kinetic term if you perform the Berezin integrations, which essentially will give you 2 epsilon symbols, right? And then you do all the contractions if you want and stuff like this, will give you this, and they will give you this, and they will give you also for the P forms and the scalars and whatever you want. So this is a very nice way to write very complicated Lagrangians or gauge theories in a very simple form. Moreover, it highlights the fact that these Lagrangians are gauge invariant. Because gauge invariants, which for a P, Q tensor would be d of a P minus 1, Q parameter plus d to idle of a P, Q minus 1 parameter is basically obvious here. So this kind of gauge transformations were also shown by Henning on Monday. So here it becomes obvious that this kinetic term has this. Moreover, one can write if yes.
Is there a way to generalize this to not Lorentz manifolds, to not Minkowski space, to curved Lorentzian manifolds?
Well, we haven't looked at this in detail, to tell you the truth, but I will comment a little bit later on something related. So if you can be a little bit patient, I will maybe comment collectively about this later. Mm-hmm. So if one wants to write also a mass term would be trivially easy. I mean, it's just omega star omega with this generalized hot star. So if you write here the graviton, this would spit out the Fritz-Pauli term, which is these 2 terms with this relative factor. So I think this is a nice way to write a number of known things, but also to generalize to any arbitrary P, Q tensor. Now, but let's go to something a little bit more difficult. So kinetic terms and mass terms maybe are too easy. So, and this maybe was the original motivation that we had to look at this formalism. So this is the so-called Galileon higher derivative interaction terms. So what are these beasts? So these are the answers to the question of what is the most general theory you can write in flat space-time for a single field, for example, with field equations which are polynomials in second derivatives of the field. Strictly second derivative of the field at this point. So no undifferentiated fields, no once differentiated fields, and no more than 2 derivatives. But polynomial in second derivatives, right? So the answer to this question for scalar fields is given by the so-called Galileons, which were described in 2008 by this gentleman here. And naturally, and this explains also the name of the theory, naturally they are invariant under this characteristic symmetry, so they have shift invariance. So I'm talking here about the scalar fields. They are shift invariant, but also their derivatives are shift invariant, right? So this is like a generalized pseudo-Nabu-Goldstone boson, so generalized pions in a way. Now, originally, the Lagrangians that describe these interactions were found by these people in 4 dimensions for scalars, and they are this. So this is the interaction for 3 fields, this is for 4 fields, and this is for 5 fields. And of course, I don't expect you to read through because this is, of course, very complicated. Now, the funny thing is that these are Lagrangians, right? And then when you vary with respect to phi, you find polynomials in second derivatives as field equations. Now, later, these Lagrangians were cast in a more controllable form by Defayet, Desser, and Esposto Farese, and they were generalized also to differential forms. Now, what our goal was first of all to understand how to write this very complicated stuff in a way that highlights what is the structure behind that, and in a way that you can remember it maybe, and also to generalize this for mixed symmetry tensor fields, so to ask whether there exist these kind of interactions for mixed symmetry tensor fields. And here is the answer. So I'm still talking about bipartite tensor fields, and I will call them tensor Galileons. So essentially, I mean, we give like in quotation marks, the interpretation of this being sort of some generalized kinetic terms eventually. In which sense? So including the kinetic term that I described before, these interactions for any P, Q bipartite tensor in any dimension, they are included in this formula here. So it's a finite sum from n equals 0, which gives the kinetic term, to a maximum value of n that I will discuss shortly, of some quadratic stuff here, which has the generalized Hodge, which uses the inner product with the generalized Hodge operator. Now, this omega n plus 1 is this combination here. So it's omega times d to the omega to the power n. So you see that this has n plus 1 appearances of the field. So here, this Lagrangian that I wrote has an even number of field appearances. You will ask, of course, in the previous Lagrangian for scalars, there was also 3-field and 5-field terms, right? Of course, this reproduces the 4-field term for the scalars, but of course, this works for anything, for all P, Q bipartite tensor. You just write it down, and you can ask your computer to do the Berezin integration. I mean, it will spit out something very long, right? Now, in the special case of P equals Q, for example, for scalars and gravitons, or the 2,2 tensor that was discussed as one of the exotic supergravities yesterday, on Monday, there is an enhancement of the possibilities. So basically, apart from this quadratic term, you can also introduce this quadratic term where this funny notation shifts by 1. So these are odd fields. So actually, there is an easier way to write all this. So there is again a sum from n equals 1, this time to n max, of this very simple thing here. So it's just omega n plus 1 times the Minkowski metric to some power. And this one, if you expand it for scalars, for example, in 4 dimensions, it gives you these 3 Lagrangians that I showed in the previous transparency, but you can do it in any dimension for any field. Now, of course, this is an overstatement because you cannot do it in any dimension. There is a bound on the number of appearances of the field, and the bound is set by the fact that you cannot really write whatever in some particular dimension. So the maximum value of field appearances for a P, Q bipartite tensor is given by this in terms of the dimensions, and by this for the special case of P, P. Moreover, something that I could have already mentioned, these interactions, they don't like bipartite fields whose sum of P and Q is odd. This is obvious in our formalism. This was also shown in this more complicated way by trying to write things as total derivatives. But in our formalism, it's just obvious because if you go here, and if you have even 2 here, and this is an odd thing, this is just 0, right? Because we are talking about degree 1 stuff, or odd degree stuff. So for P plus Q is equals odd, these interactions don't exist. Although for odd, one could also point out that there are higher derivative topological terms appearing here, which we would like to study, but we haven't studied them yet. Now, but for what does this exist is for the graviton for sure, and in fact we have shown that for the graviton, it reproduces an answer that was known from the 70s. In particular, it reproduces the Lovelock invariance. So the same question that was asked for the scalars before, it was asked for the graviton in the 70s by Lovelock and answered by these generalizations of Einstein, of general relativity to higher dimensions, which contain higher orders of the Riemann tensor. And this exactly reproduces this invariance. Moreover, they also exist for 2 forms, for example, because P plus 2 plus 0 is 2, it's even. So 2 forms have these interactions, but from 7 dimensions and higher. Good. Maybe a last word about this Galilean stuff. First of all, you can study you can use a generalized version of the Poincaré lemma, essentially to study the symmetry. Let me find again my, You found it? Ah, I found something. Okay, good. You can study the symmetries. Of course, for P equals Q equals 0, the symmetry is just this, C plus BI xi. Both C and B are constants here. So this is the essence of this Galilean symmetry, right? Because it reminds of Galilean symmetry, of course. Well, yeah, of course, they are relativistic theories. Don't get confused about that. And then for P-forms and for bipartite tensors, the symmetry changes. Of course, there is this gauge symmetry that you have here. And moreover, there is this extra symmetry that depends on the bosonic coordinate x. So this is sort of the generalization of this second part here to P, Q tensors. I should stress that for irreducible tensors, this symmetry takes you out of irreducibility. It doesn't respect irreducibility. So maybe one should forget it for irreducible tensors. And let me also mention that there exist a number of generalizations of what I presented here about Galileons, which are very elegantly captured in this formalism that we have. And the generalizations are, first of all, you can have multiple interacting species of any type. You can very easily write down a general form of what the Lagrangian for these interactions would be. And this would allow also fields with odd degree to participate in these interactions. It's just that they cannot have interactions among themselves, self-interactions. Secondly, you can generalize this quite easily to field equations up to second order, not only strictly second order, so with first order derivatives and with undifferentiated fields. And this maybe relates a little bit to the comment of Thomas. So you can generalize these Galileons to curved space-time. So this is a complicated matter because essentially what happens is that in flat space-time derivatives commute, but in curved space-time derivatives don't commute. So what you have to do is that you have to add counter terms in your Lagrangian that involve the Riemann tensor so that you can guarantee that, the theory will be second order in derivatives. And once you do it was shown by these people here that once you do this for the four-dimensional scalar, you discover again the so-called Horndeski gravity theories, which were the answer to the problem of describing the most general scalar tensor theory with second-order field equations. Now, for bipartite tensors, this is more tricky business, and we do not have a complete answer whether you can always write them in curved spacetime. And now, maybe if there is some question up to now on this stuff, I'll be happy to answer. I will move to the discussion of duality. So let me go slowly, maybe in the same spirit as in the previous part. Let me present first to you some formulas that are known and they have been derived in coordinate form. And then I will discuss how you can unify these formulas in a nice single biparametric Lagrangian that contains them. So we talk here about duality. Typically, duality is realized at Lagrangian level, so off-shell, via some master Lagrangian or parent Lagrangian for two independent fields, out of which one is a Lagrange multiplier field. And then integrating out each of them leads to dual field theories and implements some duality relation. So this is what we do for two-dimensional scalars when we do T-duality. That's what we do for photons when we do electric-magnetic duality and all this. So let's discuss first the well-known case of the dualization of a P minus 1 form to a D minus P minus 1 form. So in order to do this, you consider a first-order Lagrangian that contains a P form and a P plus 1 form. This P plus 1 form is the Lagrange multiplier. And then you write down a quadratic term in this F, right? And then you write down this term that contains dF and the P+1 form lambda. Now, once you take the lambda equation of motion, this essentially gives you the Bianchi identity for F, and then it sends you to the second-order field equation for a differential form P-1. When you take the F equation of motion, you obtain a duality relation. And then you solve this duality relation, you implement it back into the Lagrangian, and you find a different Lagrangian, which is in terms of a D minus P-1 field, which is the star of the P+1 form. So, for example, this is exactly what we do in 2 dimensions for P equals 1, so for scalars, and this gives us the R to 1 over R T duality when you have a single scalar. This is also exactly what we do in D equals 4 for 1 forms, and this gives you the inversion of coupling, the E to 1 over E, let's say S duality, so this strong weak duality. And in particular, the duality relation is, of course, of this form on shell, so it exchanges F with the star of the field strength, so you have the field strength of the P-1, and then on the other side, the field strength of the D minus P-1, and they are related by Hodge duality, by this partial Hodge duality. And moreover, we know very well that in this setting, Bianchi identities and equation of motions are mapped to each other, so to equations of motions and Bianchi identities for the dual field. This is rather obvious. Now, some similar story exists for the graviton, right? So here is the dualization of the graviton. So the graviton I will think as a irreducible 1,1 tensor. So then you consider a master Lagrangian which contains a 2,1 tensor and a 3,1 tensor. However, these ones are reducible. So we consider 2 reducible fields here, and the starting point is this Lagrangian here. So, which is a little bit more complicated than before. It's again a quadratic term in F, but it has several terms with fixed relative coefficients, and it has also this term with a Lagrange multiplier. And then when you take the Lagrange multiplier equation of motion, you get the linearized Einstein-Hilbert axiom back. In fact, you have to think here that there is an antisymmetric part that enters the game, like a Kalb-Bramont field, but this cancels out algebraically. So the calculation shows that this doesn't contribute. It only enters through total derivative terms. Then when you take the F equation of motion, you obtain some duality relation, and then this leads to a dual Lagrangian for a D minus 3,1 irreducible tensor, which is the partial Hodge star of not of the 3,1 Lagrange multiplier here, but of its traceless part. Because, of course, you need an irreducible field, and of course, this is not the dual of the star of this is not an irreducible field. The star of its traceless part is an irreducible field. For example, in D equals 4, here the graviton would go to a dual graviton, much like the photon goes to a dual photon in 4 dimensions. In D equals 5, the graviton will go to the Cartwright field. So this is where the Cartwright field enters again. This was shown in this paper here by Mark and collaborators. And maybe, for string-oriented people, in 10 dimensions, you get a 7,1 field. So this 7,1 field typically is something that you expect to couple to the magnetic dual of the graviton, so to the Kaluza-Klein monopole. Now, the duality relation in this case, the on-shell duality relation, was described by Chris Hull here. So there is, again, a similar story. So you have essentially a linearized Riemann tensor, and this is exchanged by the partial star of it. So the linearized Riemann tensor is d twiddle of the graviton. The dual one is d twiddle of the d minus 3,1 of the dual graviton. Here, the exchange of equations of motions and Bianchi identity is a little bit more tricky, though. In particular, these 2 tensors satisfy 2 Bianchi identities, right? dr equals 0 and d twiddle r equals 0. And they satisfy an equation of motion, which is well, the Einstein equations, trace r equals 0, right, for free field. So here, the Bianchi identity d to idle r equals 0 is mapped to the Bianchi identity d to idle of the dual field strength curvature, if you want, being 0. And then the irreducibility of the curvature tensor R, which is sigma r equals 0, is mapped to the equation of motion. You can easily see it by the definition of sigma. So if you remember, sigma is star trace star, right? So when you replace r with star r, this will give you trace r hat equals 0. So the irreducibility is what is mapped to the equation of motion. And finally, the Bianchi identity dr equals 0 and the equation of motion trace r equals 0 give you the second Bianchi identity of the dual tensor. So this is a little bit more tricky than before. Finally, there is something called exotic duality, which was argued by these people here, at the very least, based on work of Chris Hull also. So let me do it in an example. So here you take a two-form again, and essentially you try to see it as a bipartite tensor, as I mentioned in the beginning, which has a trivial slot, and you try to do duality on the trivial slot, right? So what these people considered was this Lagrangian here in terms of a 1,2 and a 2,2 tensors. So these are reducible, both of them, and the lambda is again the Lagrange multiplier. And they considered this Lagrangian here with these particular factors also. So then they showed that when you take the lambda equation of motion, the result is again the kinetic term for a two-form. So this was true also for this one here. So this Lagrangian also gave the kinetic term for the two-form, right? But then there is a second one, which also gives the kinetic term for the two-form when you integrate the Lagrange multiplier. But now what happens when you do the equation of motion for Q? So what happens is that you get a theory for a d minus 2,2 object in d dimensions, which is again the star of the traceless part of the 2,2 Lagrange multiplier. Now, in that case, the duality relation on shell is a little bit different. So it is actually not very different. It's the same, the blue part. So it is again it's an exchange of R with its star, with its partial star. But this time, you think of this as so this R here is a 1,3 tensor, right? And this R hat here is related to this d minus 2,2 field. So the fields change. But now what happens? Now, if you start from irreducibility, and irreducibility here means sigma twiddle r equals 0, because Q is greater than P. So when P is greater or equal to Q, it's sigma r equals 0. When Q is greater or equal to P, it's the other one. So irreducibility, which is sigma r equals 0 and holds, does not map to trace r hat equals 0. Actually, you calculate trace r hat, and it's not 0 explicitly. But is that bad? Well, okay, I mean, what you find instead is that the third trace of R is 0. Of course, R hat is something that is d minus 3,3, d minus 1,3. So the single trace doesn't do much. It is the third trace that would give a correct equation of motion. So what happens here? Because the third trace cannot be an Euler-Lagrange equation of any Lagrangian. So this tells you that in order to implement this duality relation in the Lagrangian, you need additional fields of shell. And this is simply because of this fact. Okay, I will not continue like this. One can do the same thing for the double dual graviton. This means dualizing the graviton, which is 1,1 to a d minus 3, d minus 3 mixed symmetry tensor. You can do it for the Cartwright field. You can dualize the 2,1 and actually in two different ways. right? Because there is a duality on the first slot, on the second slot, or actually in 3 different ways, because you can do both. And you can do it for higher tensors like generalized gravitons and whatever. So what we wanted to understand is whether all these seemingly different looking starting points have some sort of common origin. And indeed they do. And it becomes very transparent in our formalism, I think. So we have a single 2-parameter Lagrangian, which is first order, which describes all the above that I mentioned, and I will discuss in a little while what precisely when precisely it gives the dualization. So let's look at this first. So this contains just 2 terms, right? So the first term is a quadratic term in a p, q reducible tensor F, which will play the role of the field strength on shell. We use here the generalized Hodge star that we used also in the kinetic term. And we have here some operator, which is described by this calligraphic O. And this operator, it is, well, we know this operator in closed form. It depends on the 2 cot race operators. It acts on p, q tensors so that it takes, so that it satisfies this equation. So it acts on a d omega, for example, and it picks only the irreducible part of the mixed symmetry tensor. And then it can contain some additional up to d twiddle exact terms, which are irrelevant because they are total derivatives when you plug them in the action. So basically the role of this is that when you take when you integrate out the Lagrange multiplier, you get a Lagrangian for an irreducible tensor, not to contain additional fields. So this is the role of this calligraphic operator. And for example, for the graviton, this operator looks like this, just to give you a flavor of it. For the Cartwright field, depending on which dualization you want to do, it looks like this or like this. It always is some sort of combination of sigma and sigma twiddle. And the point is that when you write down this, when you use this operator and you write down this term and do the Berezin integration, you find essentially all the starting points that have been described before. And the second term, it contains also this Lagrange multiplier, which is a p plus 1, q mixed symmetry tensor, which is reducible again. And this one is given in terms of the other inner product with a product of the 2 partial Hodge star operators. So this is the underlying Lagrangian, the underlying parent Lagrangian that describes all these dualizations. And in particular, these are the admissible domains. So there are 4 domains of values for which this Lagrangian gives you everything. And these domains are basically for q equals 0 and q equals 1. So then P is in some large domain of values also. So in the q equals 0 case, you start with, it's the standard P form duality, right? You start with a P minus 1 form and go to a D minus P minus 1 form. For the q equals 1 case, it's the standard graviton duality. You start from a P or generalized graviton, let's say, duality. You start from a P minus 1, 1 tensor and go to T minus P minus 1, 1. Then for P equals 1 and Q in this domain, you start with a Q form and you go to a D minus 2, Q form. So these are the exotic dualities. And then for Q equals 2, for P equals 2 and Q in this domain, you start with a like generalized graviton 1, Q and go to D minus 3, Q. So in that case, actually, you can show that this includes the double duals of the graviton. Now, some comments is that for the first 2 domains, the dual dynamics follow directly from the Lagrangian. However, as we discussed earlier, for the exotic cases, there are additional off-shell fields. Right? So this is discussed in detail in this paper here. It was mentioned by Olaf also in his talk. And then the dual dynamics does not follow from the Lagrangian. So what you have to do is you have to eliminate the additional fields on shell. This is exactly because this third trace, for example, of the Riemann tensor, of the generalized Riemann tensor being 0, cannot come from a Lagrangian. Secondly, all necessary cancellations that happen can be proven in full generality using general identities. You don't have to expand ever anything. You just use identities that all these operations satisfy. And maybe I should mention that, in fact, apart from these 4 domains of values, there is also another domain that you can use this Lagrangian for, and this is the case where p equals 0. So this p equals 0 is a strange case because, of course, when p is 0, then you don't have, d of this, so then you cannot, the Bianchi identity cannot be solved in terms of some, there's no -1 degree form. But what happens here is that this gives certain mass deformations that can be used, for example, in cases where you have domain wall branes, like in type 2a, in the massive type 2a. And a final comment about this is that in suitable dimensions, you can also add topological theta terms. So in the self-dual dimensions, for example, you can also add topological theta terms and also do this procedure. For example, in 4 dimensions, you can add the theta term, and then it gives you the S part of the SL to Z duality, so tau goes to -1 over tau, where tau is the complexified coupling, which has theta and T. This is work in progress, and it's part of also some more general work in progress with Yorgos and Arash Ransba, which is that we are now doing the multiple field generalization of this procedure. And in fact, the multiple field generalization, as you might expect, leads to some sort of higher Bush rules, because this is exactly the procedure. So when you consider multiple fields in 2 dimensions for scalars, this is exactly the starting point for finding the Bush rules, right? What we read in the book. However, this procedure works also for other fields in other dimensions, so there do exist some sort of Bush rules for other fields in coupling space. So this is work in progress, which I'm happy to discuss after the talk. And in the final 6 minutes or so, I would like to revisit a little bit parts of what we saw in the duality part of the talk. So recently, there was, or like 1 year ago, there was a very interesting paper by Mark and collaborators stating that the double dual graviton, so this d minus 3, d minus 3, does not provide a truly new description of the gravitational field. And in particular, they showed that in 5 dimensions, where you have 3 candidates, you have the graviton, the dual graviton, which is the Cartwright field, and the double dual graviton, which is a 2,2 tensor. 2 of them are algebraically related, which means that there is no exchange of field equations and Bianchi identities. So this is not really an independent description. So I would like to depict this like this. So 1,1 and 2,2, which is the double dual graviton, are essentially equivalent. So you can think of this as a commutative diagram of a sort, right? So that, this duality is this duality and an equivalence. So this also has the corollary, let's say, that there are no doubly magnetic solutions. So there are only 2 types of sources. So this is really a duality, it's not a triality, which I believe was already known to Chris Hall back in 2001. And then we asked the same question for the exotic dualization of a differential form. In other words, let's take a 2 form in 10 dimensions, because this sounds very stringy, and it's actually something that people have used. So there are 4 duals in principle, right? So there is a 2 form. There is the standard magnetic dual, which is the 6 form, which I will denote. So the 2 form I will denote as A with 0 here, the 6 form as B with 0 here, And then there is the exotic dual of the two form, which in 10 dimensions will be an 8,2. I will denote it like this. And then in principle, you can also find the exotic dual of the 6 form, which is this one here. So there are 4 candidates. So the question is, how many of these are really independent? And the answer is again 2. And not only that, but these people here have argued that one can continue doing this exotic duality, to higher and higher mixed symmetry tensors, and essentially unveil an infinite chain of duality relations. And, well, you can ask the same question for this infinite chain, and the answer is again 2. So the infinite chain is just 2 large lines of equivalencies, but the duality is really a duality at this level. Let me go into some more details about this. So in order to kind of give you a flavor of how this can be shown, let me first present a very unorthodox approach to standard duality between a P form and a D minus P minus 2 form. So the unorthodox part of this approach is that instead of considering their reasonable field strengths, which will be the D of them, I will consider some sort of Riemann tensors. So I will think of a P form as a bipartite tensor of P, 0 type, right? And then I will define a sort of Riemann tensor like this. So this is a P plus 1, 1 thing. Now, the field equations and Bianchi identities of this are, well, the Bianchi identities are obvious. They are dr and d twiddle r equals 0. Now, the field equations are trace r equals 0, which are Einstein equations, right? Well, of course, this is a P form, like it's a P form, right? Satisfying Einstein equations, you would say. Actually, this is very nice because the equations that the P form satisfies, of course, is that d star d is 0, right? But then there is a very beautiful identity which says that d dagger twiddle, so this is, so if you act with a star here, so this is d dagger d equals 0, right? But then d dagger, actually d dagger is d twiddle trace plus trace d twiddle in our formalism. You can prove this identity. And then this identity is exactly what turns like the Maxwell equation into an Einstein equation. Funny, right? I mean, this is just equivalent. It's just a funny approach. Now, the dual tensor is defined in the standard way. So you take the partial Hodge star. So it's just presented here in terms of like these Riemann-like tensors. And it satisfies the Bianchi identities that you expect and the Einstein equation that you expect. And then the potentials here are related by the expected Hodge duality. So the P form and the D minus P minus 2 form are related by this one, which you could have found in a much easier way than this complicated way I showed. But then why did I show this way? Well, the point is that then you can ask the question, how are the other 2 dual fields related? So essentially, the dual field with the exotic dual field, right? And then this approach that I presented in the previous slide becomes very useful because then you can define a new irreducible tensor, which is by degree d minus 1, p plus 1, as the transpose of star twiddle of the second partial Hodge duality of the original Riemann tensor. And this actually can be related to this Riemann tensor for the dual field. And it can be related by means of the product of star and star twiddle. So in a way, the dual field with the exotic dual field have a double duality relation. And much like the graviton and the double dual graviton, which become equivalent, these 2 fields become equivalent too, for basically the same reason. You can directly show that B, this is, I remind you, is the exotic dual and the standard dual are basically the same, differing by p powers of the metric tensor. So this is an algebraic relation. So there is no, whatever equation satisfies one satisfies the other, it's not an exchange. So this essentially means that the duality is there, the exotic duality, you can do it, but you cannot kind of at the same time think of the standard dual and the exotic dual as two independent things, because they are one and the same thing. And this, we checked it also for the corresponding sources. Of course, they also end up being proportional, and you can easily extend the same logic to higher duals. And 1 minute maybe beyond my time, so let me conclude. So first of all, well, our main remark is that we have this formalism based on graded coordinates, which I think simplifies very much a lot of complicated expressions, and it also highlights their common origin and gives them a geometric flavor. And on top of that, it offers a tractable path to search for generalizations, for example, in the context of interacting higher derivative theories, where we find some new interactions there. And in the last part, I discussed how you can also, using this formalism, provide a general treatment of many, or if you want all in a certain domain, standard and exotic dualities. And as part of my outlook, well, I already mentioned that we are working on a similar Lagrangian for multiple fields this time, at least for multiple fields of the same degree, right? And try to think about what would be the corresponding relations between the couplings in the two dual theories. Another thing that we are looking at regards topological terms, and whether we can use, of course, topological terms can be useful in many contexts, so we are thinking about a number of applications. So we had a recent paper with some applications in gravitoelectromagnetism, which I invite you to take a look. And finally, to put it in a broader picture, and maybe this is something that was also somewhat mentioned by Olaf in his outlook, I would be very interested to think about whether these mixed symmetry tensors can fit in this context of higher gauge theory, maybe in the approach of Melchior and Thomas, where they discussed towers of differential forms and showed the relation to Q manifolds and L-infinity algebras. Maybe somehow we could include also the mixed symmetry tensors. And I will conclude with that.
Thank you very much. Other questions?
So when you say multiple fields, you mean like 3 or more fields that are all still PQ bipartite mixed symmetry tensors, right?
Well, I mean, so for two-dimensional scalars, if you consider one field, you get R to 1 over R.
Yeah.
But then when you do string theory, you consider multiple fields. Like
right, okay, 26, so you get some
right?
like T-duality with spectators and things like this. Is that the...
So you consider 26 fields, right? So this is what I mean.
Okay, but you're dualizing along all of the fields at the same time, right?
Yeah, but I mean, okay, you refer to spectators, yes. I mean, you can choose to dualize a subset of the fields,
okay,
of course.
Yeah, that was my question. Thanks.
Well, I have two questions. One is about the last part of your talk, where you have this non-orthodox presentation of P-forms with curvatures that contain one extra box in one extra column. So that means that these curvatures contain two derivatives. Is there a way to motivate that by some new symmetry or something? Because the standard curvature, you want to have some gauge invariant object. Now here you might have a bigger invariance, I don't know. Is there any way to understand these non-orthodox, I mean this Riemann tensor for a P-form in terms of symmetries?
Yeah, that's a very interesting question. I'm not so sure we have thought about it because, I mean, the main thing we just thought is that we can use this very beautiful formula to turn the Maxwell equation into this Einstein-like one. Well, I would expect that the symmetries, of course, remain the same, that you don't really have any extra symmetries. I mean, I don't vouch for that, but I wouldn't expect any extra symmetries. Maybe if one can try to ask the question whether the corresponding, like if you can do this for non-abelian theory, for example, this might be an interesting thing. But I don't know if it would work.
Okay. And then the other question is, did you consider higher spins with more columns? I mean, 3 columns, 4 columns?
Yeah, so this is a very fantastic question, of course, and I had about 10 minutes of my talk on that, but then I thought I would not have time to talk about this, so I erased it. So yes, the short answer is that we tried to look if there are some sort of Galileon-like interactions for higher spins. And the short answer is that for fully gauge invariant and local, we didn't manage to find anything. We did not manage to find them.
Okay.
So we do not have a proof because it is rather complicated, but I am pretty much convinced that they do not exist local and fully gauge invariant Galileon-type interactions, even like gauge invariant meaning linearized for higher spins. You can write down, because there are a number of criteria you have to satisfy. You can write down gauge invariant but not local. Essentially, you will have boxes in the denominator that you will not be able to cancel, right? Which they do cancel for the kinetic term, but for these ones, they will not cancel. So there will always be some term that they do not cancel. Or you can manage to write down something without inverse boxes, let's say, which would be local, but you cannot respect all the symmetries. Okay. So it's one or the other.
Thank you.
Are there more questions here? Or online?
Yes, I also have 2 questions. One is about this 2 Hodge duals. So normal Hodge duality on a general manifold, you need a volume form and a metric. So you have like this star and star twiddle. Are they also defined in this setting?
Yeah, so of course we have been working on flat space, right? So this is mainly our concern in this particular work. So now you're asking whether you can do it in a general manifold, right?
Yes.
Well, I believe you can define it. Yeah, we haven't done it, but I believe that one can define it in a very similar way.
In the same context, right?
Yes, yes. I believe that you can define it in the same way. I haven't done it, but...
The second question relates to, it's something I also asked in the talk of Olaf. If I understand these dualities correctly, then essentially you always use at some point that something close is also correct. You say that like, you have some equation of motion, d star f is equal 0, or star f, so that means star f is d of something. Is this correct? And what happens if the space-time is not simply connected, so that the Poincaré lemma doesn't apply?
Okay, yeah, so of course, in what I referred in this talk, I've always been using the Poincaré lemma, so you are right in your expectation. Well, okay, apart from the fact that, for example, when you introduce sources, you cannot always do that, right? I don't know, for non-simply connected, of course, this may be a little bit more complicated to answer it. But even here, like in the last part of my talk, we have done this analysis also in the presence of sources. So when you have sources, you cannot use the Poincaré lemma, which means that basically you cannot introduce sources for both of them. So you have to choose one or the other. I don't know if this helps at all for your question.
I didn't hear in the end a bit. There was some connection issue. But can one correct it if the space-time is not simply connected, these dualities? Say even without any
Without sources?
Yeah, can one correct it if spacetime is not simply connected? If there's no Poincare lemma, can one still save these dualities?
Yeah, well, I have no good answer to that at the moment. I mean, I can promise you to think about it, but I do not have an answer.
Thank you. That's all.
Can I ask a question?
Sure, go ahead.
Yes.
Yeah. Can we formulate the universal first order action in terms of Q manifold, like AKS sigma model? Yeah, I'm interested in the
yeah, maybe you can.
With,
yeah, it would be great if you can formulate it in a more mathematical way. Yes, well, but up to now, this is what we have where we have reached, and of course we've been thinking about different directions. But yeah, I don't know is the answer, I guess, at the moment.
maybe, yeah, I guess the condition in inconsistency condition of gauge symmetry should be given from the Q square equal to 0 condition. And like or it's related to Kreutzmann-Strobel's works. You mentioned in the last page of.
So in the Kreutzmann-Strobel, yeah, there is a Q square equals 0, and that's enough for everything. Now, I don't know what happens if you introduce mixed symmetry tensor in the game. So probably you would have to use like the similar logic of thinking of an ideal, right? So that you have some Bianchi identities that form an ideal, and then you define your Gates transformations to be the most general possible, but now including these mixed symmetry tensors, or at least, you know, including one of them first, and then see whether you have some sort of Q square equals 0 condition. Yeah, but I don't know the answer.
Thank you.